Katrina here, and today we're going to talk about matrix inverses. So this is an important topic in linear algebra, so make sure that you watch to the end and please subscribe for more videos. So let's look at the definition of what the inverse of a matrix actually is. So the inverse of a matrix is denoted as a to the power of -1. And we have it such that a multiplied by its inverse, so this is a matrix multiplication, is equal to the multiplication of the inverse multiplied by the matrix. So here it shows that the order doesn't matter. And after you perform this matrix multiplication, you end up with the identity matrix, where I is the identity matrix. And the identity matrix is a matrix that has just ones down the center and it has zeros everywhere else. So this is an example of a 3x3 identity matrix here. So that basically tells us that if you multiply a matrix by its inverse, you're almost like canceling out all of its values so that you end up with the identity matrix, which is one down the diagonal. But you have to make sure and be aware that not all matrices have inverses. Only some matrices do. This should remind you of our discussion about determinants, so please make sure to check out that video if you want more information. So let's go over the conditions that have to be met in order for a matrix to have an inverse. So the first condition, just like a determinant, a matrix must be square. So a square matrix has some dimensions n by n. So that means that the number of rows has to equal to the number of columns. So that is our condition number 1. The second condition that has to be met is that the determinant must be not equal to 0. So the determinant of A cannot be equal to 0. If the determinant equals to 0, then the matrix is not invertible. So those go in both directions. So if the determinant is not equal to 0, then the matrix is not invertible. If the matrix is not invertible, then the determinant is not equal to 0. And this goes hand in hand, our third condition here, that tells us if the determinant actually is equal to 0, then the matrix is what we call to be singular. And if a matrix is singular, then that means that it is non-invertible. Okay, so today we're going to look at how to take the inverse of a 2x2 matrix, and I'm going to give you an overview of how to take the inverse of a 3x3 matrix. So let's dive in. So let's first consider a 2x2 matrix. So the land of 2x2 is definitely the most friendly when we're trying to take these inverses. So let's start by looking at some matrix A, which has entries A, B, C, D. So the inverse of A is given with the following formula. So remember, this is our notation. We write a to the power of -1, and this equals to 1 over the determinant of A multiplied by a matrix where we swap the values of our A and D entries and we make our B and C entries negative. So you can see right away here why our determinant cannot be equal to 0. Because if we have a determinant equal to 0, then we'll end up with some 1 over 0 term in front of our matrix. And we know that if you divide 1 by 0, you get something that is undefined. So that's why it would not be able to have an inverse. So that is always the first thing you want to check, because that will save you the hassle of actually calculating it if you determine that it cannot even exist in the first place. And in my previous video, I showed you how to calculate that determinant for a 2x2 matrix, but let us just refresh our memory. So the determinant of a 2x2 matrix A is calculated by multiplying our A and D entries together and then subtracting the multiplication of our C and B entries. So here we want to be looking at our original matrix A, taking these values and doing this multiplication. So remember, our condition over here is that the inverse exists if and only if. So this IFF is if and only if our determinant of A is not equal to 0. And I have to keep stressing this because this is a very important property. So now let's go ahead and actually look at an example of how to find this. So in our example, we have a matrix A that has values 4, 7 for its first row and 2 and 6 for the second row. So our step 1 is to compute the determinant of A because we want to determine whether the inverse actually exists. So we can see that condition 1 is met. So this is a square matrix. So we've passed condition 1. So now let's just determine whether it's invertible or not by seeing if we have a non-zero determinant. So we can calculate this determinant pretty simply since it's a 2 by 2 matrix. So that means we just take our AD entries and subtract our BC entries. So that means we have 4 times 6 minus 2 times 7, and this gives us 24 minus 14, which equals to 10. And great, 10 does not equal to 0, so we're all happy about that. So then that means that the matrix is invertible. So that is great news. So that means we can go ahead and apply the formula to find the inverse. So that is our step 2, and we're going to look for the inverse. So recall it is 1, so we have our A to the negative 1 equals to 1 over the determinant of A, and then multiplied by the matrix of negative D and A, and then negative B and negative C. So that means that we get 1 over 10 multiplied by 6, negative 7, negative 2, and 4. So this is how we apply this. So now that we have this 1 over 10 on the outside, this is a scalar multiplication. So that means that we apply this 1 over 10 to every single entry in this matrix. So watch here. We now have then 6 over 10, negative 7 over 10, negative 2 over 10, and 4 over 10. And then you have an option to leave it in its fraction form, or you can take it a step further and you can simplify this and do the calculation to get a decimal form. So we'd have 0.6 here, negative 0.7, negative 0.2, and 0.4. And there we did it. We found the inverse of A for our 2 by 2 matrix. So that is great. So the next thing I'm going to show you is just the step-by-step of how to find an inverse for a 3 by 3 matrix. So this process gets a little bit lengthier once we get up into this third dimension. So there's 2 different types of strategies that we can use to find this. So one strategy is called using the adjugate method. So this is one way, and the second way is to use something called the Gauss-Jordan elimination. Oh, it's Jordan with a J. Jordan elimination. So my preference is to use the second one, the Gauss-Jordan elimination. However, some people are taught instead to use the adjugate method. So I will leave this for another video because this will take quite a bit of time to go through this whole process. So make sure that you stay tuned to find out how you can take the inverse of a 3x3 matrix. I'll be walking you through a step-by-step way how to use the adjugate method and the Gauss-Jordan elimination method. So I hope you enjoyed this video today. It gives you a bit of a head start how to find the inverse of a 2x2 matrix and the two methods we can use for a 3x3 matrix. Make sure to also understand the conditions that it has to be square, and if the determinant is not equal to 0, then we can find the inverse. However, if the determinant is equal to 0, we have a singular matrix which is non-invertible. Okay, that was a lot of information. Make sure you have it all written down. If you enjoy this video, please give it a like and comment any questions you have below. And I hope you subscribe so that you can see more of my fun math videos. And I look forward to seeing you next time.